Thank you. Okay, so so why are we? So these are the particular areas that we're going to be kind of looking at. So on the wire checksums themselves, some additional cleanup in how the checksums are done, some additional algorithms that we're doing there, and then some improved performance based on some hardware availability, if possible. And then on the opposite side of that, some portability improvements. If the hardware is not available, that you can still use the same, a wider variety of these checksum algorithms. On the end-to-end part, the important characteristic for us is that it uses the T10 DIX standard, and that allows the disk hardware to actually take over the checksumming, so that we don't have to do the checksumming on the server CPUs. Also, there's an interesting feature that we're kind of including along the way. It's called version mirroring, and I will talk a little about that later. It provides additional protection to RAID systems. So, what's the point of these features? The most important point is that the end users know that the data that they want written gets written, so that nothing along the way, corruption on the network, bit flipping, bad code on the servers or the clients or whatever, is messing up their data. The version mirroring provides some additional protection against RAID failure modes. Again, our goal, as I said, was to offload the heavy calculations off of the server, so the server is able to scale with more and more clients, so that we have faster and faster throughput rates without having to touch the data on server CPUs. And then again, to support a broader variety of interoperability options between servers and clients that have different hardware. So first, the bulk checksums. A little history. Originally started with a CRC32, which is a heavily popular standard from IEEE and ANSI. They like that one a lot, so that was the original one that Lustre started with. We added Adler 32, which is a much lighter weight checksum that was easy to calculate, but people have problems with it, and they claim that there are cases that it's not a strong checksum in certain cases. Shuichi Ihara added CRC32C, which is a Castagnoli version of the CRC32 that has hardware support in Intel's Nehalem processors. So so there's a hardware patch for that actually in your new latest and greatest Lustre 2.2. And then WhamCloud has just recently, also in 2.2, added their multi-threaded client Portal RPCD, which vastly improves the single client performance by parallelizing checksums on the client. And then also, again, part of the history here is the secure Portal RPC layer that Lustre has a completely different set of checksum functions. And so part of our goal then is to clean up those duplicate functions. So we are moving in, this is in WhamCloud bug LU1201. We've moved both the Lustre checksums and the secure Portal RPC checksums to use the kernel crypto hash library, so that now it takes advantage of the entire kernel crypto library. So we don't have hard-coded stuff in Lustre anymore. So that not only enables future hardware support and whatever PowerPC customization for these particular algorithms that may happen to show up in the kernel, we would kind of get for free now in Lustre, and also the wide variety of items that are already in Lustre, that are already in the kernel, can be used now in Lustre very easily. Also, we've added CRC32C software support by doing this, which allows for a client that has, for instance, that doesn't have a Nehalem processor to use to run the algorithm in software. The idea being that if you have enough clients all doing this in software, you're still going to be I/O bound, and you can still take advantage of the I/O of the hardware version of a CRC32 on your server. So that's the kind of the interoperability case, the wider variety of hardware support. And then also we've added, so in Intel's latest version of their CPUs and their Westmere processors, they've added a hardware instruction called the carryless multiply. That's what the CLMUL-QDQ is about, carryless multiply, which allows for coding efficient coding of various checksumming algorithms. So that includes, so what we've done is we've added a CRC32 hardware-based algorithm using that code and are pushing that into the kernel. And then also, actually, this provides support for this CRC 16 T10 algorithm as well, so that can also be pushed into hardware. And I will talk a little about that later. Okay, so what do we get out of that? The purple is the guy that's in Lustre 2.2. The yellows are the ones that are coming into 2.3. So these are local rates of running checksum on a single thread on a single processor. So these are the throughput rates basically that you can get just on a single node. So this is the local access, and then IOR results will hopefully also show improvements, but these are just the local algorithm. And then on the top of that graph, you see some kind of common usages of those guys. So these should go basically about these are now going as fast as the Adler checksum, so that should be show some benefit for people that we're trying to stay away from the CRC32 stuff because of the speed. Okay, so end-to-end data integrity. Now that I've told you about the improvements on the over-the-wire checksum, I'm going to tell you we're not going to use them. First, a little background of T10. T10 is a standard that provides for additional protection information tacked onto the end of hardware 512 byte or up and coming 4096 byte sectors on the hard drives themselves. The hard drives are available today. We're shipping them. You can get T10 support in hardware. So what the T10 support does is it provides three fields on the end of every 512 byte sector. There's tacked on another 8 bytes, so now there are 520 byte sectors. But one is a checksum, it's the GRD field. The second is an app tag, which is a kind of a user available data. And the final field is a reference tag, which provides the location of where that data is supposed to reside on disk. And so, as I said, there's support for this in drives, and there's also support for this in some HBAs that also verify the same information and or fill in information depending on what exact flavor of T10 you're using. Here's kind of a graph of, sorry, did I have it? Yeah, okay. Here, a graph of where that protection lies. So the little blue arrow is where the T10 diff standard covers. So that's the original T10 diff standard covered just from the HBA to the drives, where the HBA calculated the information and the drives verified that the checksum was correct and that the location that the data was being written, whereas where the disk drive is actually writing it. So that verifies against some two particular types of problems, which is corruption between data corruption between the HBA and the drive, and potential software error somewhere along the way that sent the data that was intended for a particular place on the drive to an incorrect place. So this would verify that original data wasn't overwritten because of that, and also verifies that the data is getting to the right spot that you want for later. Okay, so what later, after T10 diff standard was produced, there's a T10 DIX, which is data integrity extensions, which provided a broader protection envelope. And the original idea behind T10 DIX was to provide that protection envelope all the way from the application all the way down to the drive. So the user in fact, in the D10 DIX standard, is capable of generating checksum data themselves, embedding that again with a standard with a write IO call, and that data would be passed all the way back down, potentially verified along the way by the operating system and the HBA again, and then finally verified by the disk drive, so that the end user, basically the application writer, is absolutely certain that the data that they wrote is the data that got to the drive, without anybody in the middle kind of messing with the data itself, and also verifying that the algorithms for calculating the checksums and all that don't really matter, because the hardware at the disk drive in the end is doing that verification. So as long as the hardware at the end is doing it right and the application at the beginning is doing it right, you absolutely know that that data is getting to the drives. So how do we do this with Lustre now? We add some more steps along the way, but again, our goal here was to extend that data protection envelope all the way from the application to the drive. You can see the current coverage with Lustre is just that orange triangle, basically, that goes over the network between the OSC and the OSS. And we're using, again, that DIX standard to potentially pipe the information all the way from the client now down over the wire from the OSC to the OSS, and also down from the OSS to the disk. So those two additions provide, again, that complete protection envelope, so that you can again verify that, hey, the data that I wrote as an application made it to disk with the same absolutely the same checksum. So what does this involve in changes to Lustre? There are additional checksumming data now that need to be transferred. So because we're transferring the checksums from the original application, we have to transfer all the checksums, which is this 8 bytes of protection information with each 512 byte sector. So that's not an insignificant amount of data. Right now, Lustre checksum over the wire, the orange guy, is only 32 bits or whatever it is, small amount of information. And right now we're doing 8 bytes per sector, which is a lot more. So we have to transfer that additional information. So that's one potential area that needs to change, and that can be done in a couple of different ways, and we haven't quite decided what the best way to do that is. One way would be to include that data in the bulk descriptor, so that the original RPC that comes from the OSC to the OST could include that protection information. The other would be to transfer it as additional bulk information, so that the bulk transfer hardware would take care of it. The second change would be adding the protection information and checking to the data path on both the client and the server side. This is just basically the plumbing of the data going through Lustre. This is actually not an issue, but for memory map pages where potentially the data can change before the checksums, in between when the checksum is calculated and when the data is sent out of the wire, we need to be able to send back a return code saying, hey, the data changed, you've got to recompute the checksum again and send us some new data. Simply disabling the bulk checksum since they're no longer needed. And then the final point, and again, this is back to what I was saying before, is we can actually turn off the GRD checksums along the way, all the red check marks there, except for the very last one, and you're still guaranteed that the data that you wrote in the original application has been checked before it's written on the hard drive. So you can potentially turn off those two check marks on the server side that are running, well, sorry, the one check mark, I guess, that's running on the server itself, and therefore avoid touching or looking at or calculating anything on the OSS to avoid the CPU overhead. Okay, so now I'll talk a little about that version mirroring feature. So there's a very interesting paper called Parity Lost and Parity Regained, written by an Andrew Krukov et al. that talks about 6 different failure modes in common in RAID systems. So the first is latent sector errors, where the data is no longer readable basically from the drive. Second is data corruption, when data gets corrupted on the drive. It's still readable, but it's corrupted. The third is misdirected writes, which is again what that T10 ref field was kind of about, where data gets sent to the wrong spot. Torn writes are when lost writes first is when data that the drive claims that is wrote never gets written in the first place, and either due to power off or some other strange occurrence. Torn writes are kind of a subset of that, where part of partial pages get written, or parts of data in a transaction get lost, again probably due to power failure or something like that. And then the last case is parity pollution, where data that is that has been corrupted, where when one set, so in a RAID system you have redundant data and your original data, and parity pollution is where you incorrectly assume that one or the other is the authoritative correct data, and correct using that, when in fact you are wrong, and you're using bad data, bad parity to reconstruct data, giving you again corruption. So those are 3 kind of classes of outcomes. You can either recover your data when you detect things correctly, and your parity, you choose the reconstruction path correctly. The second class is data loss, where you realize that the data is lost, but you can't do anything about it. You can at least report an error to the client saying, hey, we lost your data, sorry. And then the worst case of all is, of course, silent data corruption, where you don't realize that anything has been messed up, and you just go ahead, sadly using wrong data, and no one's the wiser till your simulation crashes. So what is version mirroring? So version mirroring is basically a way to address those 6 areas relatively simply. So the idea here, and this is kind of both a description and an application here together. This is a RAID stripe across disks and then the parity disk. And just a little background here, blocks and little definitions. Blocks are is the chunk of data of one disk, and then those are typically made up of multiple sectors in each block. So our idea here is to take combine these 2 kind of concepts of the version mirroring and the T10 app field to store that version information, so that we can get that versioning more or less for free without having to store it any other place in the file system. The idea basically is to store on each chunk a version number, and on the parity block a version vector, which is basically just the collection of those different version numbers. And then for illustrative purposes, here's an example of a lost write. When you have version mirroring, what happens and how you can correct it. So for instance, in this case, we're updating block C, for instance, by writing new data there. So we try to write C prime, the new version of C, and P prime, or P of the parity block based on A, B, and C prime. So we write this, we think we wrote it, but in fact there was a lost write. And for instance, C got lost, and the parity was updated, but not block C. Later we come to try to attempt to update block A, another partial stripe write. So the first thing we do when we do this, and depending on what way your RAID does reconstruction, it's either you reread B and C or you just read P, but the eventual outcome is the same. You read B and C for preparation to construct the new P prime. You check the version information along the way. You see, hey, wait a minute, version of C is no longer, doesn't match the version in P. P has a later version. I know that that's the correct, that parity block therefore is correct, and that C is the one that got lost. I can reconstruct C now, and then I can rewrite my new A. correcting the data basically along the way. So what have we covered with this? The latent sector errors, again, the drive typically detects those. For data corruption, we have the T10 GRD checksum on the for each one of the blocks, for each sector within the block, as well as the RAID parity block for doing data reconstruction when an entire chunk. So the GRD checksum tells you what block was incorrect, and the parity block in your RAID system enables you to correct that data. This is an easy way to verify that the data is correct because the verification of that GRD checksum is done again on the drive, so the drive tells you, hey, this data is bad, and so all your RAID system needs to do is, okay, the drive told me the data is bad, I just need to go fix it. Again, the server CPU doesn't need to do anything about it. Pretending if you have MD RAID, then your server CPU has to reconstruct the parity, but that's only for these strange cases. So in general, your CPU doesn't have to do all this checking. For misdirected writes, you have the ref field again in the T10 standard, so that that protects against the data being sent to the wrong spot. For lost writes, what we do is we store. For lost writes again, just like this, we've stored the version vector, so we can see any block that gets lost. We can reconstruct it as we're doing these reads. For torn writes, so when a sub block is lost, so say for instance that just one sector out of one of these blocks is lost, since the version information is encoded in each sector, you can, as the sectors are read, as a block is read, each sector is just verified against the next sector in the block, and if any of them have a version that's lower, again we've determined that we're missing the data there, and we can reconstruct the torn writes that way. And the parity pollution, again, because of the GRD and the versions, we can determine anything that's corrupted. We can immediately determine which version of the corrupted data is the latest, it contains the latest data, and we can reconstruct the correct block and therefore avoid the parity pollution problem. That's all I've got. So I don't know if I'm how much time I have left. I have no idea.
Let's take a question if there is one.
I know we're right before lunch, so we can all just run out of here if you'd like.
Anything? Anyone?
We got one over there from Evan.
Are you looking forward to large blocks? We just heard Andreas talk about someone's working on 4 meg writes. How does that work with your CRCs and going to the T10?
So interestingly, we are working on the large block writes as a partial enabler for this feature, for this functionality. So the large block writes not only enable you to send descriptions for 1 megabyte IOs, it also allows you to send descriptions of arbitrary blocks of data. So one of the arbitrary blocks of data that we had intended to use there was the checksumming block, basically. So the chunk of data that we're using, the T10 checksums, would be stored on the client basically as data, and then transferred again using that same 4 megabyte mechanism as another chunk of bulk data. So that was actually kind of the reason for that. It means more checksum data. So if we decided not to do that and instead put all the checksumming data in the original RPC, it means those RPCs are larger. We're transferring more data in that, but there's no. I don't think there's any problem with. There's no complication with including both those things together.
Nathan?
Yes. Who is that?
Hello. So Nathan had mentioned at the start that this has been discussed a lot in the OpenSFS TWG reflector, and I want to remind people that if you're not a member of
raised a hand.